Hey, and welcome everyone to another video in the Scientific Workflows lecture series. Today I want to talk about efficient R programming. In this lecture you will learn how you can measure the speed of your code and find bottlenecks, and we will also look at some basic but also more advanced techniques how you can make your R code run faster. So let's get started. Now, before we start, I just want to mention the main reference I was using for preparing this talk, which is a great book about efficient R programming. And you can read this book for free. I linked the book in the video description. So if you want a more depth explanation of topics that I'm going to discuss or more examples, you will find them in this book. I want to start this talk about efficiency by talking about the question, well, what is efficiency? Speaking in very general terms, efficiency is the work that gets done in a given unit of effort. And with respect to programming, the first thing that comes to mind is probably something like computational efficiency. Computational efficiency means things like how much computation time does the computer need to perform a specific operation, or how much memory does it use. But on a second thought, there is another aspect to efficiency in the context of programming that I called here programmer efficiency. And this type of efficiency is related to questions like how long does it take to write code, to maintain code, but also to read and understand the code. Now, there are always trade-offs and synergies between these different types of efficiency. For example, the fastest code might not be the most readable one, but maintainable code might be fast at the same time. And there are really different levels on which we can talk about these topics of efficiency. On a very fundamental level that has nothing to do with programming yet, we can think of an efficient setup of our tools, which can make us as programmers more efficient. But then we can also think about our project structure and our coding style and how we can make these parts of the project more efficient. And then on the top of the pyramid, we can actually talk about the functioning of our R code and how we can make it run faster and optimize it. But today, since time is limited, I only want to focus on the top part of the pyramid and talk about principles and tools to make our programming more efficient for the computer. But please keep in mind that the other aspects are just as important, if not even more important in a lot of cases. Now, if you want to know more about the first two levels, please check out my talk with the title What They Forgot to Teach You About R. It was the first talk in this lecture series, so maybe you even attended it, but I'll also put a link in the video description. And if you follow this link, you will find a lot more details, practical tips, resources, and examples regarding these important topics. But now let's get started with the topic efficient R code and code optimization. So now we will answer the question, how can I make my R code run faster? Before we do this, I want to pose another question. Is R slow in the first place? And the answer to that question is yeah, R is kind of slow compared to other programming languages, especially languages like, for example, C++. But very often this is not really a problem. And R is a language that is designed to make programming easy and not necessarily fast. So you could say that this slowness of R is actually more of a design choice than a flaw of the language. In addition, R is also not designed to be particularly memory efficient, but R is fast and memory efficient enough for most daily tasks. Otherwise, of course, we would choose another programming language from the start. So before we start optimizing our code and make it faster, we always should think about the question, should I optimize in the first place? And here I want to start with a quote from the Advanced R book by Hadley Wickham, because I think that it nicely summarizes this issue. What he's writing in this book is that it's easy to get caught up in trying to remove all the bottlenecks in your code. But you should not do this because your time as scientists is valuable and is better spent analyzing your data and interpreting it, not eliminating all of the possible inefficiencies. So when you're optimizing, be pragmatic. Don't spend hours of your time to save seconds of computer time. And this is something that you can always keep in the back of your mind when you think about optimizing your code. So to decide whether it's worth optimizing your code in the first place, you need to think of these questions here. How much time do I save by optimizing? How often do I run the code? Because of course, if you run your code only once, it's totally fine if it takes 15 minutes longer and you just take these 15 minutes and have a coffee with a colleague. But of course, if you run this code every day, the situation looks very different. And then there's of course also the time you have to put into optimizing. How much time do you spend optimizing? And as I already mentioned before, very often there is a trade-off between readability of your code on the one hand and efficiency of your code on the other hand. And you have to balance these things depending on what's most important for your project. Now, I would argue that very often in scientific projects, readability is more important than efficiency, because as scientists, we ultimately want to publish our code and we want others, collaborators, but also other scientists to read and understand our code and to build on our methods or to reproduce our results. So readability is something really important. And then it's often not important if the code maybe takes 5 minutes longer. But of course, there are also projects where efficiency is really paramount. So if you have thought of all of these points and you decide, yes, my code is too slow, I want to optimize it, then you can go through the following steps. The first thing you can think about when your code is too slow for you is, can I run the code somewhere else? Because very often the problem with slow code is not the speed of the code itself, but the fact that it's blocking your computer and you can't do anything else at the same time. For this, RStudio has a nice and easy feature called background jobs that I quickly want to show you, because sometimes this simple feature can already be enough to free your RStudio environment and to run our code while your script is running in the background. Okay, so now here you can see one of my RStudio projects, and I opened up one dummy script here that simulates a script that takes 20 seconds to run. So I'm just printing something, then I'm setting the computer to sleep for 20 seconds, and then I'm generating some output background result, which is just a vector, and then I'm printing that the background results are finished. So just imagine that this is a script that runs for, let's say, 20 minutes or something like this. Now, if I want to run this script in the background and do some other R stuff at the same time, all I need to do is go to background jobs down here and start a background job. Now, first here I can select the R script that I want to run in the background. You can see that the correct one is already selected. You can set the working directory, but usually the default should be fine here. You can run your job with a copy of the global environment, which is not what we want to do now. And we want to copy the results of our background job to the global environment. And then I can just start my background job, and you can see that now it started. I have this nice progress bar, and while it's running, I can just move to another R script like this one, and I can just run code. So here, for example, I produced a plot, and you can see by the progress bar that my job is still running in the background without cluttering my R environment. And now when the progress bar is gone, you can see that the background job has now finished, and you can see that it took 20 seconds in total. And when we look at our global environment up here, you can see that the background results, which was this result vector that was produced by the background job, is now copied to our global environment. Now, of course, very often this will not be enough if your code is slow, but sometimes this can be a very fast and easy solution to just not optimize your scripts, but just run them in the background if you are using RStudio. But of course, very often this might not be enough. And you can also think about running your code on another computer, for example, on a high performance cluster. But of course, this requires slightly more effort. Now, if in the first step you thought about whether you can run your code somewhere else, and you still decide afterwards that your code is too slow and you really want to speed it up, then don't just start in the beginning of your script and go through your entire script or program. First, you need to identify the critical, so the slow parts of your code, and then you only optimize these bottlenecks. But of course, before you can optimize the bottlenecks, you need to learn how you can identify the critical sections of your code. So what we will look at now are the methods called profiling and benchmarking. And with these, you can measure the speed and the memory usage of your code. Okay, so let's start with the profiling method. With profiling, you can find speed and memory bottlenecks in your code. So, for example, you can detect sections in your code that are particularly slow and therefore worth optimizing. For profiling in R, you can use the profviz package. Using this package, you can profile a section of R code like this. First of all, you need to install and load the profviz package. Now, let's say I have a data frame with 150 columns and 400,000 rows. And now let's say I have this data frame and I want to do some operations on it. I want to calculate the mean of every column and then put them in a vector and then subtract the mean of every column from each value in the whole table. Now, this is the code that does this. And now if I want to know which are the speed and memory bottlenecks of this code, I just need to wrap the code inside of the profviz function. Because I have multi-line code, I also need to wrap the code into these curly braces inside of the profviz function. And now when I run this, the profviz package will give me a profile of all of the lines of code that are wrapped inside the function. But let's look at that in practice. Here you can see my RStudio project with the code I just showed you on the slides. So first of all, I want to load the profviz package. Next, I create the data frame, and now I run this calculating the mean and subtracting the mean from each column in the table wrapped inside of the profviz function. And when I run this, RStudio will open a profile of the code for me. Now let's make this a little bit bigger here. Now what you can see here is actually a lot. First of all, here on the top, you have a so-called flame graph. Here on the left, you can see all of the code that you ran line, and you can go through it line by line. And here on the right, you can see first of all in this column how much memory is freed here on the left and how much memory is used for every line of code. And in the second column, you can see how much time is spent in every line of code. Now at the bottom here, you can see something similar. This is a bit more complicated, but on the x-axis, you can basically see the time. And here you can see the so-called call stack. So you can see that here the apply function under the hood calls different other functions. For example, the mean function, because inside of apply, here we call the mean function. And this takes roughly 1/3 of the whole apply call, while another third of the time is taken by a function called aperm.default, which is a function that is called behind the scenes by the apply function. So this is how you can really track which function is calling which other function and how much time it takes to run this function. If you want to go in very detail, you can also go to the data view here, where you can really zoom into every function and you see for every function how much memory is used and how much time. But most of all, this here is important. So here we can already see that most of the time of our code is actually spent in this apply function. So if we wanted to look for a way to optimize this code, this would be a good place to start, because this line of code is the one where R spends most of its time on. In addition to calling the profviz function in RStudio, you also have a nice feature for profiling up here. So you can see a profile button up here, and you can just click start profiling. Whenever you want to profile, then you run all the R code you want to profile. And when you are done running the code, you stop profiling, and RStudio will also open such a profile for you. So there are different ways of profiling with R and RStudio. Let's move on to benchmarking. Benchmarking is a method with which you can compare different code snippets and functions to see which one is faster. For example, if you have two functions that fill a data frame with 1000 rows, then you could do it in two different ways. So here you have f1 that fills a data frame in a loop, and here you have function 2, which fills the data frame directly with vectors. Don't worry if you don't understand everything about the code immediately, because we are not really interested in the details of these functions now. Just know there are two different functions, f1, f2, that both achieve the same thing. Now, if we want to compare these two functions, we can use an R package called microbenchmark. Now, if you want to use this package, the first thing you need to do is you need to install it, and you need to load it using library. And then the microbenchmark package just has one function inside, which is called microbenchmark. And inside of this function, you can compare different functions. So here I'm calling f1 and f2 from before, but I'm giving them two names, old old and new, just so I can recognize them in the microbenchmark output. And here I tell the function to run both of these functions 10 times. The default is 100. I just brought it down to 10 because I didn't want my slides to take so long to compile. So what microbenchmark is doing is it's running each of these functions 10 times and then saves the benchmarking results in this variable here, compare functions. And when we look at the result, you can see that we get this table, one row for the old version of the code, function 1, and one row for the new version of the code, f2. And you can see the distribution of time it took to run both of these functions. And you can see immediately, if you look at the mean and median time it took, that f2 is considerably faster than f1. Of course, here we are still at the unit of microseconds, so this is not much time in absolute, but of course, as the examples become more complex, these time differences mean a lot more. In addition to these tables, you can also look at benchmarking results using ggplot. For this, you can just load the ggplot package and use the autoplot function to look at the results from a benchmark. And then it will give you these violin plots where you have the time it took to run the code on the x-axis and the different versions of the code on the y-axis. And here you can immediately see that the new code has much lower runtime than the old code here. Okay, so now we know how we can identify bottlenecks using profiling and how we can measure code speed using benchmarking. So now it's time to optimize our R code. Now, of course, there are thousands of options to optimize your code, and the best solution depends, of course, on your specific problem. So it's impossible to show you all of the different options that you have, but what I want to show you now is some basic things that you can consider, some typical data analysis bottlenecks and how you can avoid them. And then we will talk about some advanced optimization methods like parallelization and using C++ in your R projects. First, let's talk about some basic principles that you can always keep in mind when writing R code. The first one is vectorize your code. Vectors are central to R programming, and R is really optimized for vectorized code. Vectorized operations in R are implemented directly in C and Fortran, which are the underlying languages below R. So below the surface, R is actually written in other programming languages, which are much faster than R itself. So the faster you can get to these low-level programming languages like C or Fortran, the faster your code will be. Vector operations can very often replace for loops in R. So if there is a vectorized version of a function that you know of, then use it. For example, let's say we want to calculate the log of every value in a vector and then sum up the result. Then we have different ways to do this. So first of all, here I create a vector with 1 million values, and then I compare two different versions of the code using microbenchmark. In the first version, I use a for loop where I loop over every element in the vector. I take its log and I add it to the previous sum. In the second example, I use vectorized functions where I just take the log of the whole vector, which automatically takes the log of every element, and then I sum them up using the sum function. Now again, if you don't understand both of these versions completely, that's not a problem. You will still get the main point of this example. Looking at the benchmarking results, you can immediately see from the mean and median runtimes that the vectorized version of the code is much faster than using the for loop. And here you can also see another advantage because the vectorized code is much more readable. If you just have the sum and the log function, you can immediately see what's going on, while with the for loop, you really have to look at the code and think about what is happening here. So if you know of vectorized functions like the sum or the log function in R, then use them. Now let's take a second to talk about for loops in R, because you might have heard about this rumor that for loops in R are really slow and you should avoid them. And this is partially true because for loops in R are relatively slow and it's easy to make them even slower with bad design. Often for loops are used when vectorized code would be better, like in the example I showed you just now. For loops in R can often be replaced by functions from the apply family, for example apply, lapply, but there are also others. Vectorized functions like the sum function, but there's also a function, for example, called call means and so on. or vectorized functions from the POR package, like for example, map. So depending on your programming style, there are different ways of replacing for loops with other functions. But for loops are not necessarily bad, and sometimes for loops can be the best solution, and they can be also more readable than vectorized code in some situations. And especially if you are coming from other programming languages where for loops are more central, you might also be prone to using more for loops in R, which is totally fine. You might think of replacing some of your slow for loops with other functions. Another basic principle you can keep in mind is that you can cache variables. So if you use a value multiple times, store it in a variable to avoid recalculation. For example, let's say you have a matrix and you want to calculate column means and normalize them by the standard deviation. Then here first I create a matrix with 1000 columns, and then I use microbenchmark to compare two versions of the same code. In the first version, I do not cache the standard deviation of the matrix. So I use the apply function here to calculate over the columns here. I calculate the mean of the column and divide it by the standard deviation of the entire matrix. Again, if you don't understand all of the code, that's no problem for this example. Just note that X here is our matrix. So we recalculate the standard deviation of the entire matrix every time we calculate the mean of one of the columns. Now in the second example here, I use caching. So I create a variable, standard deviation of X. That variable holds the standard deviation of the matrix. And then I use the same apply function, but this time I don't calculate the standard deviation every time. I just use the cache value from the variable. Looking at the benchmarking results, you can see that with caching, I am 16 times faster than without caching. And of course, the more complex your examples become, the larger the difference will be. Now, moving on from the basic principles, let's talk about efficient data analysis. The first thing that is important is that you have an efficient workflow. So prepare the data, you have to be clean and concise for analysis. This helps you to keep an overview, but also to avoid unnecessary calculations on parts of the data that you don't really need. Also, save intermediate results. Don't rerun time-consuming steps in your data analysis if you don't need to. For example, if the data preparation step is time-consuming, do the data preparation once, save the already prepared data somewhere, and then you can skip the preparation step the next time you come back to your analysis. And last but not least, use the right packages and functions that make your workflow faster. Now let's look at some of these packages. And start with reading data, which is always the first step in a data analysis workflow. In this example, I have a CSV file on worldwide emissions of greenhouse gases, which has around 40,000 rows and 7 columns. Now, the base R functions that you probably know to read CSV files are, first of all, read.table and read.csv. These functions are perfectly fine to read CSV files, but they might become slow if your data file is really large. And for this, there are many alternatives to read data. For example, there is read_CSV from the readr package, which is part of the tidyverse, and there is fread from the data table package. So let's compare some alternative reading functions. First of all, here I define the path to my CSV file, and then I use microbenchmark to compare the 3 different reading functions. First of all, I use read.csv from base R, and I use read_CSV from the readr package, and third, I use fread from data table. Please note that these additional arguments that I give here and here are just for the purpose of benchmarking. Usually you don't need to give these when you want to use the functions. Now, when we look at the results here, we can clearly see that read CSV from base R is always slower than read_CSV from the readr package, and fread is even faster. And please keep in mind that although these differences now are small on the scale of milliseconds, they scale with the size of your data. So if your file is really large, then I always recommend you to use fread instead of the other functions. Another thing you can do when reading your data is the bottleneck is using plain text data, because reading plain text data is much faster than, for example, files like Excel files. Here I use microbenchmark to compare read CSV and read Excel, both from the tidyverse. And when we look at the results, you can clearly see that reading a CSV file is much faster than reading an Excel file. And also this scales with the size of your data. Now, of course, for smaller data files, it's totally fine if you want to keep using Excel files, but for larger data, use something like CSV or TXT. txt. Similar to the reading functions, there are also corresponding writing functions. In base R, you might know the functions write.table and write.csv. And also here, the faster alternatives would be write_CSV from the readr package, so tidyverse, or fwrite from the data table package. Now, when you read your data into R, then the next step is data manipulation. And also here you have different packages that offer fast and efficient data manipulation and analysis. For example, you might know the dplyr package from tidyverse. This package has a C++ backend and is often faster than base R. Then there is the data table package that you already know now, which is very fast and memory efficient. But the downside here is that the syntax of data table is quite different from base R and tidyverse. So if you want to use it, you have to learn this syntax. And then there is the collapse package, which is C++ based, and it's specifically developed for fast data analysis. And the cool thing about this collapse package is that it works together with both a tidyverse but also a data table workflow. And in collapse, many functions are similar to base R or dplyr functions. They just use the prefix f for fast. For example, there is an fselect function or an fmean function. And this makes it really easy to adopt this package. So let's look at two examples where using these packages might give us a speed boost. First of all, a very common data analysis task is summarizing data by group. In this example, I want to summarize the mean carbon emissions from the electricity sector by country. And I want to do it using, first of all, data table, then dplyr, and then collapse. Now, here you can see the data table way of doing this. First of all, we need to convert our data frame to a data table using setdt. So here you can already see that using data table needs a different syntax. And then I just wrap the operation in a function to make it easier to compare it later using microbenchmark. And here you can see how you can calculate the mean of the electricity sector by country. So this syntax might not be familiar to you if you're not familiar yet with the data table package. Now next, here you can see the dplyr way of doing the same thing. We take the greenhouse gas emission data, we group by country, and then we summarize the mean of the electricity sector. And last but not least, the collapse way of doing the same thing. We take the greenhouse gas emissions, we group by for fast grouping, then we fsummarize for fast summarizing, and we calculate the mean using fmean for fast calculation of the mean. So you can already see that the jump from dplyr to collapse is really, really easy because you just have to put f's in front of all of your functions. And looking at the results, you can clearly see that using collapse makes your code much faster than using dplyr or also data table. And all of this just by putting f's in front of all the functions. Now let's look at another example where I compare selecting different columns from the data. In the first example, I used the select function from dplyr. In the second one, I used the data table way of selecting columns. And in the third, I use fselect from the collapse package. And looking at the results, you can clearly see that again, collapse is much faster than all of the other options. So to conclude, you can easily switch from using dplyr to using collapse if you have sections in your data manipulation that are particularly slow and that you want to optimize. If you are in need for even more advanced optimization, you can turn to methods such as parallelization or using C++ inside of your R scripts. And this is what we are going to look at now. Let's start with parallelization. By default, R works only on one core, but CPUs have multiple cores. Now, to find out how many cores your computer has, you can use an R function from the parallel package, which is called detect cores. And here you can see, for example, that my laptop has 8 cores available. Here you can see an example of a sequential program that runs on only one core, which is the default also for R. Let's say you have a function called runModel and you want to run it n times in a loop. Then usually you would start the program and then every iteration of this runModel function will be run one after the other until the program stops. The idea of parallel computation now is that you start the same program, but instead of running it sequentially, you divide the functions onto different cores and then run them all at the same time. So here, for example, I run the runModel function 4 times at the same time. And in theory, this should be 4 times faster than the sequential version of the same code. Parallelization in R can be implemented using the future verse. Future is a framework that helps you to parallelize existing R code in an easy and beginner-friendly way. And depending on your coding style, Future has parallel versions of the base R apply family, of different pure functions, but also has parallel versions for each loop. So if you're relying on for loops, you can easily make them parallel using for each loops. I can't go into too much detail now, so I linked 2 helpful resources about the future verse and a tutorial on the slides and also on the course website. So check it out if you're interested in more information on parallelization. But let's look at one quick example how you can easily parallelize existing R code. Let's assume we have a very slow square root function. The function that you can see here calculates the square root of a number, but before it does so, it sleeps for 1 second to simulate some heavy computation time. Now, whenever we want to run things in parallel, we first need to plan a parallel session in R and tell R how many cores we want to use for that parallel session. To do this, we can use the plan function from the Future package. So first you need to install the package and load it using library. And then, as you can see here on the slide, I planned a multi-session with 6 workers. So using 6 of my 8 available cores. Now let's look at a simple example of a parallel lapply. Here you can see the sequential version of the code where I call lapply to calculate the slow square root function for all 10 elements of this vector x. I'm using the TikTok package here to measure speed in an easy way. So I just call the tick function before I run the code and the tock function after I ran the code, and then it will print me the time it took to run the code. In this case, roughly 10 seconds, which makes sense because our slow square root function sleeps for 1 second and we have 10 elements in our vector. So we would assume that the function runs around 10 seconds. Now I can easily make this parallel using the future.apply package from the future. This package contains the parallel version of different apply functions just using the prefix future underscore. And you can see I just need to load the package and then I can use the function. And now you can see that with 4 seconds, this version of the code runs more than twice as fast. In theory, of course, it should be 6 times faster because I'm using 6 cores, but there's always some overhead in parallelization. But for more complex code examples, the difference would be much bigger between the sequential version and the parallel version. Now, the cool thing about these parallel apply functions is that all apply functions have their future version. So you can just replace apply with future underscore apply in your code to make it faster. And here you can see all of the future functions that you have available. Another thing you can easily parallelize are for loops. Here you can see that I loop over the values from 1 to 10, apply the slow square root function to every value and save the result in a list. Now, if I want to make this parallel, the first step I need to do is I need to turn this for loop into a for each loop, because for each loops can easily be parallelized. For each is a function that is available from the for each package, so you first need to install and load this package. And then you can rewrite the classic for loop into a for each loop like this. So you can see you need to call the for each function, you need to say which values you want to loop over, and then you need to use this %do% operator to start the loop. And when you look at the sequential version of this for each loop here on the left, you can see that we need roughly 10 seconds to loop over these 10 different values, which again makes total sense. Now, if you want to parallelize this for each loop, all you need to do is you need to load the do future package, and then you can replace the %do operator with the %do future operator. Everything else can stay exactly the same. And now you can see that this code only takes 2.8 seconds to run. So we save 80% of our runtime just by replacing do with do future. Now, when you are done working in parallel, you always need to explicitly close your multi-session again by planning a sequential session. This frees up your cores that you reserved for the multi-session. Now, I hope that with these examples you saw that it's really easy to parallelize some sections of your code in R. And if you're interested in learning more, please check out the FutureVerse website for more examples and tutorials. If you still don't have enough of optimization, you can go the extra mile and replace slow code in your R scripts with C++ code. But this is already rather advanced. To do this, you can use the R package rcpp to rewrite slow R functions in C++. This is also used internally by many R packages to make them faster. So you are running RCPP code probably every day when you are using different R packages. The requirements for using RCPP are, first of all, that you need a C++ compiler installed. And of course, you need some knowledge of C++ to be able to rewrite your functions in C++. If you want to know more about RCPP, you can check out this book chapter and the online documentation I linked on the slide, where you get a good overview and you have a lot of tutorials to get you started with RCPP. But let's look at one simple example. Here you can see an R function to calculate Fibonacci numbers. If you don't understand the function right now, that's totally fine. That's not the purpose of this exercise. But if we apply the function and we say we want to calculate the 30th Fibonacci number, we can just call our Fibonacci R function and it will print us the 30th Fibonacci number. If I now want to rewrite this function in C++, I can use the CPP function from the RCPP package. So I first need to load the package and then I can call the CPP function, and inside I define the same function as before in R, but using C++ language. And then I can use this C++ function in my R script just like a normal R function to calculate the Fibonacci numbers. So here you can see that now I'm using the Fibonacci CPP function inside of my R script to calculate the 30th Fibonacci number, just as I did before with the R function. Now for the people that already know C++, it might also be interesting to know that you can also source external C++ functions from C++ script. So for example, you can have a C++ script fibonacci.cpp where you define and export the Fibonacci function written in C++. In R, you can then use the source CPP function to source the C++ script and then use the C++ function just as we saw before. Now, the question, of course, is how much faster is it now to use C++ instead of R? So let's have a look at that. If we use microbenchmark to compare the Fibonacci function in R and C++, we can see that C++ is almost factor 1000 faster. So using RCPP is really powerful for slow R functions, but of course this is also a more advanced technique that you probably don't need too often for everyday data analysis. But I still find it an interesting technique to know about, so I wanted to mention it here just in case you ever need it in the future. As a summary, I now wanted to bring back this pyramid that I showed you in the beginning. And I wanted to remind you that we only looked at the top of the pyramid where you deal with efficient R code and optimization. But very often the first two levels are already sufficient because they deal with efficient setup of your tools, project structure, and coding style. And I hope that you saw that there are easier and more complex ways to optimize your code. And if you take one thing away from this lecture, it is to always keep in mind to check first your bottlenecks before you start to optimize. On the lecture website that I linked in the video description, you find some additional links and material if you are interested in more details for any of the mentioned topics. And with that, I'd like to thank you for your attention. If you have any questions, please just let me know in the comment section.